Okay, the last couple of examples of implicit differentiation here. And maybe you gave these a couple of tries on your own, and then you're just checking to see how it went. Okay, so we have x squared plus cos x equals to sine y. All right, so the derivative of x squared is 2x plus the derivative of cos x will be negative sine x is equal to the derivative of sine y. So as soon as I see that y, I have to think implicit differentiation. So the derivative of sine is cos of the argument y multiplied by the derivative of the inner, which is y, or the derivative of the argument, which would be y prime. And so this is easy to isolate. We're just going to divide by cos y. So we get 2x minus sine x as my numerator, all divided by cos y. All right, example 16. So in this one, hopefully we're noticing that we have some 2's in here. So this is actually asking us to take the second derivative. So we have to do this twice. Okay, so let's look at the first derivative. When we do the first derivative, the derivative of sine is cos, and the derivative of cos y, so there's that y, there's an alarm going off in my head, I have to do implicit. The derivative of cos is negative sine of the argument y followed up by the derivative of the inside, y prime. And so here's the answer to the first derivative. Y prime is equal to cos x divided by negative sine y. That's my first derivative's answer. And now I'm going to take the derivative of this as my second derivative. And then to take the derivative of this, it's going to require a quotient law. Okay, I'm going to do the quotient law to take this second derivative. So y double prime, that second derivative, is equal to low. So the lower function is negative sine y. Or if you prefer to work with the negative up on top, we could write negative cos x on positive sine y. It doesn't really matter where you put that negative, only put it in one spot. All right, so if I decide to put the negative up on top, I would have my lower as just positive sine y multiplied by the derivative of the upper. So the derivative of negative cos x is going to be negative sine. Okay, really, you could just write positive. Minus, so low d high, less high, which is negative cos x, multiplied by the derivative of the lower function sine y, which would be cos y multiplied by y prime. And then all of that is divided by sine y squared. Okay, so here's the calculus law done, and I'm going to try and do some tidying up. So first of all, if you think back to how we did second derivatives, we took this y prime that shows up in that second derivative and we replace it with what we found to be y prime in the first derivative. So that's the first thing I'm going to do, is do a replacement there. Okay, so y double prime is equal to, I have two negatives here, I'm going to make that positive. So I have sine x, sine y, and then I have two negatives again, so plus cos x, cos y, and then y prime was negative cos x on cos y, and all of this is divided by sine y squared, which I could write like this. Okay, I'm going to slide to my next piece of paper here. All right, so now I'm trying to think about a way to tidy this up. Okay. Oh, I just saw an error. Let's fix that. This should have been sine y on the bottom. My apologies. Hopefully you caught that and were like, Malmstrom, wake up. Okay, so the first thing I'm going to see is that I actually have a fraction in that second term. So I'm going to make the first term have the same denominator so I could try and tidy this up. So sine y on sine y to give them a common denominator. And so that would equal to y double prime is equal to sine x times sine squared y plus, minus because we have this little guy right here hidden. Okay, so I have minus 2 cos x's, so cos squared x, cos y, and then all of this is over that common denominator of sine y that I just made. And then this is divided by sine squared y. Okay, so here we are. We have sine x sine squared y minus cos squared x cos y all over sine y. And then we'll kiss and flip this, multiplied by 1 over sine squared y. And then those two sine on the bottoms can combine to sine cubed. And then on the top, what are we going to do with that top? Okay. I think I see what's going on here. Sine x sine squared y minus cos squared x cos y all on sine cubed y. Right back at the very beginning of the question. Now these second derivatives, you have to remember you're trying to always find a target to the beginning. Okay, do you remember those sneaky pieces? Cos y was equal to sine x. All the way down here in these sneaky second derivatives, this cos y is equivalent to sine x. So we have sine x sine squared y minus cos squared x. Now I can replace that cos y with sine x, all on sine cubed y. And then why did we do that? What was the purpose behind that? Well, that means I can factor out a sine x. And so I could have sine x is equal to sine squared y minus cos squared x all on sine cubed y. And then sine squared y minus cos squared x, unfortunately, is not an identity, but that would have been cool if it was. So there we are. There's our second derivative. How fun was that? Woo! We are done 7.2 part A lesson. I would encourage you to do the startup question at the beginning of the 7.2b lesson notes because it looks at finding the derivative in terms of an actual angle. So you're evaluating the derivative instead of just finding it in terms of variables. All right, see you for the next set of lessons when you're ready.